In the last section, we talked about functions that are increasing and decreasing, and how the derivative tells us about increasing and decreasing. In this section, we are going to be using the results of that to talk about maximums and minimums of functions. But first, we do need to make a distinction. If we have a function on some domain, usually an interval I, so we have f on I, we can have it that for some c that's an I, f of c is bigger than or equal to f of x for any other x that's an I. When this is the case, we could just say that f of c is the maximum of the function. But we're going to be a little bit more specific and say that f of c is the absolute maximum of the function. So if this is true, then f of c is the absolute maximum. So I'll probably abbreviate maximum minimum frequently when I'm writing them as just max and min. But f of c is the absolute max of f on the interval I, or interval or domain I. We're going to use the term absolute maximum here because we need to distinguish between this type of maximum and another one that we'll see in a little bit. Of course, we also have the reverse. If instead of f of c being greater than or equal to all the f of x's, if it's less than or equal to, then this turns into a minimum. And I don't want to have to rewrite all of that, so let's just go ahead and abuse copy and paste. If f of c is less than or equal to f of x for all x in I, then f of c is absolute minimum of the function on that interval or domain. Now, as a collective term, we're going to refer to these as absolute extrema. So you see the term up here. An absolute extremum of a function is either an absolute maximum or an absolute minimum, but we want to be able to just say it all at once. We do want to make a little bit of distinction about our terminology, though. It's say so what I want to say here is that the absolute extremum of the function is the value of the function at the point. In other words, the y value, not the x value. We can say something like f of c is an absolute extremum we could say something like that. Or if we want to emphasize the x value and not the y value, we could say something like f has an absolute extrema at c. Here we're talking about the x value of c and not the y value. But we're not saying that c itself is the absolute extrema. We're saying that the absolute extrema is at c. We can even combine these if we want to emphasize both of them, if we want to mention both of them. F has an absolute extrema of, say, f of x, or sorry, f is using c here, f of c at c. This is kind of more relevant if we have, say, f of c was a number. So we can say f has an absolute extrema of an absolute maximum of 2 at x equals 1. Something like that. But it is not correct to say that c is the absolute extrema of f. So being a little bit nitpicky here, but just want to make sure people understand the terminology. Now the problem is that our process for finding the absolute extrema for a function when we're using calculus is going to require a little bit of a detour. So let's look at a picture. Let's say we have some function, and it looks something like this. And I don't know what happens outside of our graph, but we'll just assume this is what we have. Our graph has two high points, and of course one of them is higher than the other. We have this point up here, and of course this is going to be our absolute maximum of the function, at least if we're only looking at a domain that includes what we see here. But as far as calculus goes, there's not a lot of difference in what's going on around the higher point than there is around the lower high point. And therefore, we're going to make a definition that's going to include both of these. So once again, we're going to have a function f and some c in its domain. We say f of c is a relative, let me write it all out, relative maximum of f if there is an interval, specifically an open interval, containing the c value, so some interval around the value that we're saying is where that relative maximum is located, for which f of c is a maximum of f. In other words, we're saying that f of c is greater than or equal to f of x for all x in that open interval. So if we look at what we have up here, so we have some, let's say this is c, there's some interval around c, some a to b. We can even look at the points all along our graph here. If we only restrict our attention to this section around c, that is a high point. That's still true over here. If this is a different c, maybe this was c1 and this is c2, we can still look at some interval around c, maybe, let's say from alpha to beta. I'm going to use some Greek letters here. So in this section here, the value at c2 is the maximum of the function on this part. It's not the maximum overall, but it is the maximum on some interval around c2. And that's what we're trying to capture. Of course, we can also look at relative minimums. It's just basically exactly the same thing. In fact, I'm going to go ahead and copy this like before. So I have to move on to another page to have enough room. So relative minimum. Oops. Want to be black and black. So f of c is a relative minimum of f if there's an interval around c, basically, for which f of c is a minimum of the function, which means that f of c is less than or equal to f of x for all x in the interval. In this picture here, we have a relative minimum here. I don't know, maybe this is c3 now. Kind of ran out of A, B, alpha, beta, but the point here is that around c3, it is a minimum of the function. So on some region around c3, is a minimum. It's not a minimum overall, because there's points over here and over here that are lower than it. But we're not talking about the entire function, we're only looking at a small region around C3. And technically, it doesn't matter how small of a region we need to make, we can always shrink our interval around C as much as we want. So why do we care about the relative extrema instead of the absolute extrema as much? Well, because relative extrema have certain properties in terms of calculus. If we look at our graph here, what is special about what the points that I've identified as the relative maximums and the relative minimum? They all have a specific property. If we were to look at the tangent line at each of those points, it's horizontal. We have a horizontal tangent line here. We have a horizontal tangent line here. And we have a horizontal tangent line here. If we're looking at any point that had, say, a positive derivative, a positive slope of its tangent line, our function is increasing there. So it's not going to be at a maximum or a minimum, because there's going to be points before that point that were smaller, and points after it that are bigger. Same thing if our derivative was negative. We'd be decreasing. We wouldn't be at our maximum or minimum. So when the function is differentiable at a point and it's at a maximum or minimum, then we know already what the slope at that point is, what the derivative actually is. Of course, we also could have a possibility of a function that doesn't have a derivative somewhere, and we need to consider that as well. But all this results in a theorem. If a function has a relative, now you could say relative maximum, relative minimum. Of course, we have our catch-all term of relative extremum at x equals c, then c is a critical point of f. Remember, critical point here means that either the derivative at c is equal to 0, or the derivative at c doesn't exist. And hopefully you can kind of see why that's true from what I have here. If it does have a derivative, it definitely has to have a slope of 0 at that point. If it doesn't have a derivative, then, well, calculus still kind of tells us something. It identifies that as a point that we want to be looking at. But the point of this theorem is that it simplifies our search when we're looking for relative extrema. All we have to do is identify the critical points of the function. And we've already looked at how we can do that. We were using those in the previous section, in section 3.1. But there's actually even a little bit more that we can do. We can actually use the derivative to identify what type of relative extrema is. We need to identify whether it's a maximum or it's a minimum. So we have another theorem called the first derivative test. And this is really just kind of, it's less of a theorem and more of just interpreting our charts. So here we're going to say, let's say, let x equals c be a critical point of f where f is, actually I'm not going to write this part out, but here we're going to be assuming that f is differentiable around c. We don't have some really weird function that isn't differentiable in a lot of places. Um, we're not going to force it to be differentiable at C. We want to include the critical points where the derivative doesn't exist, but we do want to say that there's at least some region around C where it is differentiable other than that point. In that situation, we have three possibilities. Possibility 1, if f is increasing to the left of C and decreasing to the right of C, which means that our derivative is positive to the left of C and is negative to the right of C. Basically, if we were to look at our number line, if we have our C on here and we have a positive derivative over here and a negative derivative over here, then what we have here is a relative maximum. Think about it in this way. If we were to look at our graph here, we were increasing before we got to C2, and we're decreasing after C2. And therefore, we had to reach a maximum at that point. At C3, we are decreasing first and then increasing. It was the other way around. So for this situation, we have a relative max at C. If we switch it around and go from decreasing to increasing, then f has a relative min. And our third possibility is where the sign of our derivative doesn't change. It's either both increasing on both sides of C, or it's decreasing on both sides of C. Basically, the two other cases of having minus on both or having a plus on both. I mean, we could have considered these as two separate cases, but the result is the same either way. We just don't have a relative maximum or a relative minimum. Usually what that means is that the function kind of stops for a second before continuing on where it was going before. A specific example where this is true is x cubed. Let's say f of x equals x cubed. Our function looks something like this. If we were to look at the derivative is actually 0 at x equals 0. And the derivative is positive both before and after 0. There is no relative maximum or minimum there. It does actually it is a critical point because we do have a horizontal tangent line, but we just don't have a relative maximum or relative minimum. So what all of this means is that in order to identify the relative extrema, in fact, identify what type of extrema they are, all we have to do is exactly what we were doing in the last section when we were finding increasing and decreasing sections for a function, and we can read all the results off that same number line that we had. I'm going to go ahead and put some examples of us doing that in the next video, though. I don't want this to be too long of a video. This first video actually turned out a little shorter than I kind of expected, but I do want to kind of section this up kind of, I guess you could say, consistently. So I'll go ahead and stop here, and we'll get into some examples in the next video.